I'd like to introduce another statistic related to the best fit line and a set of data. We've talked about the correlation coefficient, and we talked a little bit about what a best fit line does. A best fit line is trying to minimize the sum of the squares of the residuals. In the book, they refer to this, and this is fairly common notation, as the sum of the squared errors. So switching over to using the term error instead of residual, but SSE for short. So the best fit line is minimizing that SSE. And what we could do is we could compare, for our best fit line, how does our SSE compare to some sort of perfectly bad fit, I guess, as a comparison. So think about it this way. If the explanatory and response had no connection whatsoever, the worst case with you would the best fit line would just have no slope. In other words, varying this variable would predict no change in this variable. So if there's no connection, changing the explanatory is not going to predict a change in the response. So kind of a worst case scenario, no connection, would be a flat line. Now, you could make the sum of the squared errors very, very large by just moving that flat line way, way down or way, way up. So, so then there would be no bound on that. What we would do is we take the central location of this data. So there's all these y values here. And somewhere along here is the average y value, right? Each one of these dots has a y value. We could add them up and average them and get a mean. So there's the mean of all our y's. And so then what we could do is create sort of this theoretical no connection line, right? This line predicts that as you change x, nothing changes in y. It's just a flat line. So this is sort of the typical or exemplar of no association between them. Then we could compute residuals on that sort of worst case. And compare the sum of the square errors from our best fit line to this sort of worst fit line, if you will. And this computation is what we call the coefficient of determination. And actually, for short, because of the variable involved, we represent it with an r squared. The reason is actually the correlation coefficient, which we called r. Because of the way these are computed, r squared is the square of the correlation coefficient. So this coefficient of determination turns out to just be the square of what we got for our correlation coefficient. So how is it computed? Well, just as I was saying, you could take the sum of the squared errors that you get from this sort of worst case line and find the difference between it and the sum of the squared errors from our best fit line, our y hat line, that least squares regression line, and then take that as a percentage of the sum of the square errors from y bar. So let's think about what could happen here. If our data was perfect, if all this data was on a line itself, then our sum of squared errors would be 0. So we would have this worst case minus 0 over this worst case. So for perfectly linear, you would just have SSE y bar over SSE y bar, which is just 1. So on the high end, r squared could take on a value of 1. On the low end, our best fit line might be that worst fit line, right? What if we run a regression on this and we compute the best fit line and we actually get a horizontal line like this, then this difference becomes 0 because our y hat is just that y bar line. And that would be the worst, which would be the low end on that. So r squared is always going to be a value between 0 and 1. And 1 would be for perfectly linear, and 0 would be for essentially no association. If there's no connection between these two, you just get slope 0 on that line. This gives us a percentage. Right now, it's being computed as a decimal, so often you'll see the formula say, take that times 100%. All that does is just express that r squared as a percentage. You'll see r squared given as both a decimal and a percent, in which case this is between 0 and 100%. And the way we interpret that value is that that percentage is the percent of change in the response that can be accounted for by change in the explanatory. So let me write that out. R squared is the percentage of change in the response variable response variable that can be accounted for by change in the explanatory variable. So just think of the extreme case. If r squared is 1 or 100%, your data is perfectly fitting a line, which means that changing this variable 100% connects to changing in this variable, right? Because we can perfectly predict it, right? If this was just if there was an actual physical connection between these two variables and there was nothing else to be accounted for, then knowing the explanatory would perfectly tell you the value of the response because it's perfectly linear. So 100% of the change in this response variable can be accounted for by changing or a change in this explanatory. As it deviates from linear, the explanatory variable is relating to the response, so it is somehow accountable for what's happening in the response, but not perfectly, right? Because the dots are not perfectly in a line. So there's obviously other things at play that affect the value of the response, but we can quantify how much of that change in the response is because of the explanatory. We don't say cause and effect necessarily, but can be explained by that variable. And that's our r squared. And again, the reason we use that notation is it literally is, if you take r, the correlation coefficient, and square it, you get this coefficient of determination. So let's quickly, it's just a button push, but you can also get this statistic from the applet as well. So let's take a look. So here we are back in the, let me turn off the movable line. Here's our house data. Here's our best fit line. And actually, let me turn that movable line back on. The thing that the app does by default is set that movable line at that worst case situation. So it's actually putting that at a height of y bar. So that blue line is the line I was talking about before you move it at all. And so really, that's the two things that are being compared in this R-squared calculation is the residuals from that blue line versus the residuals from our best fit. And again, you can turn those residuals on and off. But down here, notice there's our correlation coefficient as we've been looking at. And if you square R, if you square 0.78, you're going to get 0.608, which as a percentage is 60.8%. So how do we interpret that number? 60% roughly of the variation in house price can be explained by the variation in square footage. So there's other variables at play in determining house price, but we can say statistically from our data that 60% of the change or variability in house price can be accounted for by this variation in square footage.